What if I told you that scientists just figured out how to solve problems that used to need million-dollar supercomputers on a laptop that costs less than your phone? Yeah, that's actually happening right now. Look, quantum physics has always been the kind of thing that makes your brain hurt. We're talking about systems so complicated that they can exist in trillions of different states at the same time. For decades, if you wanted to study this stuff, you needed either a massive supercomputer or some seriously advanced AI. But researchers at the University at Buffalo just changed the game completely. They've cracked a way to run these insanely complex calculations on regular computers. And I'm not talking about dumbing things down or getting rough estimates. I'm talking about actual accurate quantum simulations that used to be impossible without spending millions on computing power. So first, let's talk about why this is such a big deal. Quantum systems are weird, like really weird. Imagine trying to predict where a single drop of water will end up in a waterfall. Now multiply that by 1 trillion and make each drop able to be in multiple places at once. That's basically what physicists deal with when they study quantum mechanics. Here's the thing about quantum systems. They don't just have a few possible configurations. They have countless ones. And by countless, I mean numbers that would make your head spin. We're talking about systems that can have more possible states than there are atoms in the entire universe. Yeah, wrap your head around that. Until now, if you wanted to understand these systems, you had two options. Option 1, rent time on a supercomputer that costs more per hour than most people make in a week. Option 2, use artificial intelligence models that are so complex they need their own supercomputers to run. Not exactly accessible for your average research lab, right? Scientists have known for years that there should be a simpler way. In theory, many of these problems didn't actually need all that computing power. It was like using a sledgehammer to crack a nut. Sure, it works, but there's got to be a better way. But here's the catch. Knowing something is theoretically possible and actually making it work in the real world? Those are two completely different things. It's like knowing you can technically climb Mount Everest versus actually doing it. This is where Jamir Marino and his team come in. Marino is an assistant professor of physics at UB who started this work back when he was in Germany at Johannes Gutenberg University Mainz. And what they've done is pretty much revolutionary. They took something called the truncated Wigner approximation, or TWA for short. Now, I know that sounds like alphabet soup, but stick with me. TWA is basically a physics shortcut that's been around since the 1970s. It simplifies quantum math by cutting out the stuff that doesn't really matter and keeping the important bits. Think of it like this. When you're telling someone a story about your day, you don't describe every single breath you took or every blink of your eyes. You focus on what matters. TWA does the same thing with quantum physics, but here's where the old TWA fell short. It only worked on perfect, isolated quantum systems. You know, the kind that only exist in textbooks and theory papers. In the real world, quantum systems are messy. Particles are constantly being pushed around by outside forces. Energy leaks out into the surroundings. It's chaotic. The old TWA couldn't handle that chaos. It was like having a recipe that only works if your kitchen is at exactly 72 degrees, has zero humidity, and you're cooking at sea level. Not very useful when you're trying to cook in the real world. So Marino's team expanded TWA to work with what scientists call dissipative spin dynamics. That's just a fancy way of saying quantum systems where energy is constantly being gained or lost, where outside forces are messing things up, where reality is doing its thing. Their study, published in September 2024 in PRX Quantum, a journal run by the American Physical Society, shows exactly how they did it. And the results are kind of insane. Here's what really blows my mind about this breakthrough. It's not just that they made it possible. They made it easy. Before this, if you wanted to use TWA on a new quantum problem, you had to start from scratch. Every single time. We're talking about rederiving pages and pages of dense, complicated math. The kind of math that makes calculus look like counting on your fingers. Most physicists would need weeks just to set up the problem, and if they made one tiny mistake in all those pages of equations, back to square one. Marino's team turned all of that into a simple conversion table. Yeah, you read that right. A table, like the kind you used in middle school to convert inches to centimeters. According to Oksana Chelpanova, one of the co-authors who's now a postdoctoral researcher in Marino's lab at UB, physicists can learn this method in 1 day. 1 day. And by day 3, they're already running some of the most complex problems in the entire study. Let that sink in. Something that used to take weeks of preparation and required access to million-dollar computers can now be learned in a day and run on your laptop. All right, so why does any of this actually matter? Who cares if quantum simulations are easier to run? First off, this levels the playing field. Smaller universities and research labs that can't afford to rent supercomputer time can now do cutting-edge quantum research. Students can run simulations on their own computers instead of waiting months for supercomputer access. But more importantly, this frees up those massive supercomputers and AI models for the problems that actually need them. As Marino puts it, a lot of what appears complicated isn't actually complicated. Why waste a supercomputer on something your laptop can handle? The truly complicated quantum systems, the ones with more possible states than there are atoms in the universe, those still need the big guns. But now scientists can save those resources for where they're actually needed. And let's talk about speed. The new framework lets researchers input their data and get meaningful results within hours. Not days, not weeks, hours. That means faster research, faster discoveries, and faster progress in understanding the quantum world. Now, let's dig a little deeper into how this actually works without making your brain melt. The key is something called semi-classical physics. It's a middle ground between full quantum mechanics and classical physics. Think of it like this. Full quantum mechanics is like trying to track every single water molecule in the ocean. Classical physics is like treating the entire ocean as one big blob. Semi-classical physics is like tracking the waves. You lose some detail, but you capture what actually matters. This approach keeps just enough quantum behavior to stay accurate while throwing out the details that barely affect the outcome. It's smart filtering, not dumbing down. Plenty of research groups tried to do this before Marino's team. Everyone knew it should be possible. But making it accessible and easy to use? That was the real challenge. It's like how everyone knew humans should be able to fly, but it took the Wright brothers actually building a plane that worked reliably to make it happen. This breakthrough didn't happen in a vacuum. Marino worked with 2 of his former students from Germany, Hossein Hossein-Abadi and Oksana Chelpanova. The research got support from the National Science Foundation, the German Research Foundation, and the European Union. It's a perfect example of international scientific collaboration paying off in a massive way. Marino thinks this method could become the primary tool for exploring quantum dynamics on regular computers in the near future. And honestly, based on what they've achieved, that's not an overstatement. We're looking at a future where quantum research isn't locked behind paywalls of computing power, where students can experiment with quantum simulations as easily as they run any other software, where breakthroughs can happen faster because researchers aren't bottlenecked by computer access. This is about more than just making life easier for physicists. Quantum mechanics underlies everything from the development of new materials to quantum computing to understanding fundamental particles. Making quantum research more accessible means faster progress across all these fields. It means more people can contribute to solving these problems. It means the next big quantum breakthrough might come from someone working on a laptop in their dorm room instead of someone with access to a multi-million-dollar facility. So here's what you need to remember. Quantum simulations that used to require supercomputers can now run on laptops, thanks to researchers at the University at Buffalo expanding a technique called the truncated Wigner approximation. They turned weeks of complex math into a simple conversion table that physicists can learn in a day. This frees up expensive supercomputers for problems that actually need them and democratizes quantum research for everyone. The quantum world just got a whole lot more accessible. and that's going to change everything.